we're talking about machine learning again, and more from a practical standpoint, I would say, than last week. So last week we talked about what machine learning actually is. We came up with like a working definition of it. We went through like that we need to learn from samples. We need to come up with an algorithm that derives hypotheses from the data, and we introduced a little bit of like this machine learning and training loop here. I'm gonna go through step by step today and how we get our machine learning algorithms to run in a proper machine learning experiment, so that we don't have any cheating going on during the experimentation, and just so that we in the end learn something where we can make a general assumption or assessment of the performance afterwards. Because yeah, often if there are some mistakes in the machine learning experiment, you might overfit on your training data, you might underestimate the actual error that you would be making if you had new data coming in. And so that's really like something that we want to avoid. And there is unfortunately nothing more annoying than having to justify to reviewers why your performance of your algorithm is below the state of the art, even though you know that the state of the art is completely cheated and doesn't help. Like so that's really something that I have encountered in the past, and it's really annoying. So let's, as a community, learn how to do it properly. All right. We defined a general overview of a system, basically a machine learning system where you have input, we have something going on in here, and we have the outputs that we want to predict or that we want to produce through this machine learning algorithm. We have some hidden variables here that we might not model, and we have our parameters here that we want to adapt. Our model also, in addition to these model parameters that we want to adapt and like learn to optimize, it has what we sometimes call hyperparameters, and hyperparameters are these parameters that you don't really learn to adapt in a like a normal backpropagation fashion or in an error update fashion in the machine learning algorithm, but you would change those outside that like learning algorithm, and we're going to talk about this today. These hyperparameters are, for example, the number of layers in your neural network. You wouldn't adapt that dynamically during training. You adapt that once in the beginning, you train the entire system to compare the performance, then you test another set of hyperparameters, and so on. Okay? We talked about supervised learning and how we want to utilize this target signal that we are provided with at the output, and the distance or the difference between those two, our produced output and the supposed target that we need to achieve. Those are this distance kind of informs us of the error that we're making, and we had talked a little bit about like the different types of errors that we could make here. In the beginning, we were talking about toy examples, the family cars versus no family cars. We had a binary distance in this case, where you would learn if you were predicting the class correctly or wrong, but then we learned that we couldn't find out like how to find the optimal hyperparameter or a hyperplane in this case. So we needed to adapt this binary loss function to a loss function that incorporates the distance between the prediction and the hyperplane, in addition to the sigma or the sign of the output. Okay, we had some examples in supervised learning, just for reference, I guess. And we then talked about some regressions. This is also kind of like a supervised learning method, where now instead of like classes, we want to approximate a certain function. we want to approximate it as good as possible. And again, we kind of have these different types of hyperparameters. In this case, our hyperparameter would be like the order 1 of the polynomial, and in this case it would be order 2. So these are parameters that you would adapt outside the learning. Then we talked about unsupervised learning methods, for example clustering, where you want to find prototypical representations of your data within the training data that you have. I talked a couple of times already about one of our most recent developments in assessing individuals with depression. This is a vowel space measure, which is also an unsupervised learning method, which is kind of funny. We talked in depth a little bit more about supervised learning. And in this context, we mainly focus on the differentiation between generative models that are modeling the data with, for example, here, like you have one distribution for the tiger data, and down here with the blue dotted lines, you have the kitten data, and together these spread out to have this entire like probability distribution of the entire input data. And we talked about how these methods are different from the discriminative ones, where in this case you don't necessarily model the joint distribution of your labels and your input data, but you want to predict the probability of observing a class C1 given a certain input data point. And we went through two examples here. On the one hand side, we had the example of the Gaussian mixture models as a generative classifier, and the model of like a decision tree for the discriminative classes. And the decision tree, the Gaussian mixture model, that one is parameterized, so you have to identify like how many mixtures you want to have. So that's also a hyperparameter again. But then you can learn the arithmetic mean and the variation, the variance of your Gaussian mixture model from the data directly. And in the case of the covariance or the variance of the Gaussian mixture, you also have kind of like hyperparameter options there. You could have like the entire matrix or like the diagonal being just one value, so you approximate one dimension. Then you can have like a diagonal, so you learn like an ellipsoid, and so the type of depth that you go into, and like how many parameters you train also allows you to change the expressibility or the expressiveness of your method. And this kind of like also led us to statistical learning theory, where we talked about the power of certain methods and like how many points can a certain class of hypotheses shatter data points. And we talked about that lines can shatter 3 points, and we identified that this is the Dapnik-Sharp-Menkes dimension in the end. So it's kind of a theoretical tool to identify like the power of a certain machine learning algorithm. However, we found that there are a few caveats in that realm, and that in the end, what really needs to be done and what we really need to find out is like how our method compares to this certain, like the bias variance trade-off problem. And really this is kind of like where the statistical learning theory becomes a more practical problem, where if you have very powerful and very strong classifiers, you reduce your error on the training set, but you increase your variance oftentimes. And in the other way around, if you have a very like powerless, so you just learn like one linear separation classifier, you often have maybe a higher bias, so you make a lot of mistakes or some mistakes on your training data, but the variance is very low. And so we identified that this is kind of like going in the direction of an optimization problem that has kind of two parts to the optimization, and what we would like to find is kind of like this sweet spot that has a relatively low bias but also a relatively low variance. And so this kind of like is one of the issues, or one of the things that we have to deal with. So are there any questions until here? Let's just recap from last week. So, all right. So let's talk a little bit about machine learning experiments. And so what I would like to introduce here is kind of like more or less the concepts or the variables that we need to take into account. So first of all, let's look at our training sets, or like the data sets that we need to define. So on the one hand side, we have like somebody gives us a data set that has no like specific separation in the data set. Maybe if you go to a challenge data set, you will have like a predefined separation of your data set that you should be following, or that's recommended to follow. On the one hand side, the most important one, I think, is the training set, because this data set is kind of like your bread and butter data set that you're going to work with most of the time. So this one's basically used to build and construct your classifier. So you initialize a classifier randomly, maybe like a neural network, and now you start cranking your training set through. And you get already a pretty good assessment of like if this is going to work or not after a few iterations. And you would probably want to see that your loss or your training error goes down, and you can see something like your accuracy goes up, and so on. So you have these measures that are developing over the training set, and you kind of like get a better feel. Okay, so something's going on. I think I can learn this, right? So, but then the second one, what you need to do is, because you don't know if you're like training your data and suddenly you're like at 0% error, right? You're like, okay, so that's like, this is the best classifier, it can't get better. But then you want to make sure that it actually doesn't completely overfit your data. So you want to know that your data set, or that your machine learning algorithm isn't completely overpowered over your data. And then that's why you have the validation set. So this is kind of like the second most important, or the second most touched data set in an experiment. This data set you use to basically confirm your hypothesis that actually the training ran into like a place where like it gives you useful results on your validation set. And but because this is not like a process where you can basically say, okay, I trained my algorithm on the training set, then I validate it on the validation set, and you have like some result, I don't know, like 80% accuracy on your validation set. You might be already happy, which is a pretty good result. 80% is pretty decent. But then you might have an issue on the other side where that might actually not be good enough, like, or it's not the best. So what you want to do is you want to kind of like iterate over this process multiple times to find out like how good can my validation performance become. And so you might want to change your hyperparameters. So I say, I train my 3-layer neural network, I get 80% correct on the validation set, but if I do 4 layers, I get 85% correct. And now you're like, okay, so maybe there's something happening, let me increase the size of the network, go a little bit further, and so you have to iterate this process multiple times. And so this is kind of like the loop that you have to go through to find your optimal hyperparameters. The model parameters are always trained with the training set, okay? But your hyperparameters, so to say, are adapted based off of the validation performance. So that's kind of like important, okay? And then the last, yeah, so these are the hyperparameters just as like a few hints on like what these hyperparameters are. I can show you afterwards in scikit-learn what they could look like for a support vector machine. There's multiple mores. And actually also one hyperparameter in a sense like on the quotation is also the type of network you're using. You could do decision trees, you could do support vector machines, you could do something else, okay? And then the last set, and this is the one set you only use once, and that's the one set you actually report on. You report the validation performance, yes, I'm fine with that, and I would like to actually see that too. But this is the one that you're going to be evaluated on, okay? And like, again, for the project, we're not going to give grades based off of your performance in the test set. So that's, I just want to make this clear, but if you submit something to a challenge, this is the data set that you're going to be evaluated on. And this is how the state of the art is assessed. And you already can see that there are a couple of things that you need to kind of make certain of is like these data sets, training, validation, and testing set, they should all be about the same. Like you don't want them to be completely different from each other. Like if you have, for example, in a training set, you have two classes. And you have, in the very beginning of the data set, you have like 50-50 distribution of positive and negative samples, okay? And then you do a training set, and the training set has 80% positive samples and 20% negative samples. That's already kind of changing the priors in your training set towards something that is not representative of the entire data set. So you don't really want to have this happen because your model will learn this prior. Okay, it will learn to say yes 80% of the time, and you can already guess what this might run into. This can often run into like an issue where, for example, a support vector machine would always learn to say yes. It will never say no, so it basically learns nothing. Okay, so and then you have 80% correct, but that doesn't mean really anything. So we're going to talk about metrics in skewed data sets. But you want these data sets to have about the same prior distributions for all the classes, but also you want them to be quite homogeneous as well amongst each other. So for example, if you have a data set with male and female speakers, you want to also make sure that you have about the same distribution of male and female speakers in all three data sets. Okay? So there's a lot of like knowledge and preparation that goes into preparing these data sets. You don't want to put in too much because then people might get like weird about like why did you exactly do this split? Is that just because you want it to be outperforming on the test set? That's why you also want to report the validation set because you want to have that about the same balance. Okay, so this is kind of it. And then this one is never used to optimize performance. I should have probably made this bold and like red and come up in flames or something like that. But yeah, so this is important, okay? Don't do this. I know that like you might be tempted to do it for the course project, but don't do it. And yeah, just don't do it. And so never just report the best run, okay? So this basically goes into the direction of this procedure here of like training, validation, and test. That one can be repeated also. You don't have to necessarily define from the very start to the end that this is always going to be my data set, like for testing. Because sometimes, so I mean, this is the optimal way to do it for if you have the luxury of having a huge data set. If you really don't have that much data, this luxury isn't really given. So I'll show you in a second what I mean by that. I'm probably going to use the whiteboard for that. But what you can do is basically, let's just do it now. Okay. So if this is your entire data set, you can declare this the training set, this the development set or validation set. So validation and development set are often called the same. And then this is your test set. Okay? So what happens here is basically you could say, for example, I take 60% of my data for training, 20 for development, and 20 for testing. Okay? And you can randomly choose those splits. And so this is, you can name this fold 1, for example. And let's assume that this is actually sorted, okay? And then you can, for example, if you want to, you can say, I want to use this now as my training set plus this part. And then this is my dev set, and then this is my test set. Okay, so you have 20% here, again 20 here, you got 40 up here, and 20 down here. Okay, so that's your fold 2. And then you can iterate this through. And so this is basically like what I would like to see a cross-fold validation look like. Okay, if you really like want to be very careful and don't want to like kind of run into like a wrong evaluation, you can always kind of cut out the test set entirely and leave it there. But in general, you would so you would always have the test set, and you would just like have different training sets and dev sets rotate up here. But this is kind of like how you would run this experiment. Are there questions for that?
If you include the test sets as you were doing prior to this, can you overfit? I mean, because you could average out the parameter values eventually.
So that's the thing. Okay, that's a very good point. Actually, when you learn or train a fold, you like initialize, you train, you validate, you learn your hyperparameters, you report your test set. That's one fold. You like seal it up, put it in a lockbox. Then you restart the entire thing. So you basically simulate as if you had like different data sets. That allows you to kind of like run outside of the problem of having like a very bad test set in one fold, because it could happen like that you have by chance a really hard test set that you have like the poorest performance on that also overestimates your actual error. So that's kind of like maybe a help to kind of average out where your actual error is going to be at.
But then in a way you are using test set to optimize your performance, right?
No. Because you only use it to estimate. So you optimize your model parameters with this, you optimize your hyperparameters with this, and then you test with this, right? In this case, well, this was the training set before. You train your parameters with this, you optimize your hyperparameters with this, and you test with that. Okay, so, but you restart entirely, okay? Because you know, like in a parallel dimension, you might have chosen this one as your test set in the beginning anyways, right? So it doesn't really matter. But what that does do is it gives you a test performance on multiple folds that you can then average. And that's why I'd like you not to report just the best run, okay? And I would say, like, it used to be the case that everybody was doing like 10-fold of this and whatnot, but I think nowadays, like with the bigger data sets and with the models training for days sometimes, and I'm not sure if any of the groups here have like these large data sets, but if you have like data sets like this size that like really need to train for like weeks, in a sense, 4-fold or, you know, yeah, 4-fold or 5-fold is fine. Don't have to be 10-folds and wait for half a year to finish. So that's kind of that point. Are there other questions to this? You will also see very quickly that hyperparameters are models that are really complex and have many hyperparameters. Support vector machines are nice because they don't have too many. So they have, for example, they don't have like number of layers. They don't do that. But they have like type of kernel. We're going to get to kernels later on, but you could have like a RBF kernel, polynomial kernel, linear kernel, etc. And so that will be a hyperparameter. But then also you have like other variables in a support vector machine. But these more complex models, in particular deep learning models, they have different activation functions, number of layers, type of layers. Do you do a pooling or do you not do a pooling and stuff like that? The complexity of your hyperparameter search runs out of control very, very quickly. So what I would be okay with if you say we randomly initialize hyperparameters and we test 50 of those configurations because we really don't have time to run a billion, right? So that just makes a lot more sense to me. Okay, that's just like, don't think you have to run every single possible configuration on the hyperparameters. Just as a note. Okay, so here again to recap a little bit. Training, the steps in training. You estimate the parameters on training set, you tune the hyperparameters in validation set, report the results in test set. Yeah. Anything short of this yields over optimistic claims. Evaluation, we're going to go into evaluation metrics in a second. There are many different forms of evaluation criteria. And I think also, if you think back to last week's lecture, like the idea of Occam's razor is kind of like another potential idea for optimization or evaluation strategy. Sometimes you might have a performance system that needs to run like on a, I don't know, on a smartwatch or something like that. You don't want to have the biggest neural network running on a smartwatch. If you achieve about the same performance with a tiny one, you might as well just use that one. So that's also kind of like an evaluation criterion. And some issues. Okay. Yeah, so we want just add a few notes here, basically. Alright. In our case, I would like to bring in, so in our case we're investigating human communication and human behavior. I would like to bring in a special consideration that I would really like to see happen if you have the chance to do it in your data set. But basically, what we want to get at is general human behavior, general communicative performances of humans, like how do humans look like when they're sad? How do humans look like when they're happy? Okay? But then that is very different from how does this person look like when they're happy and how does this person look like when they're sad. So humans do behave very, very kind of like individually different, okay? So what we don't want to learn is kind of like these overly optimistic performances on emotional recognition or like performance assessments that involve the same person both in the training, validation, and test sets, okay? So what you want to do is you want to create those splits based off of your individuals that are present in the data. So if I say 60% goes into training, in this case, I mean 60% of all the individuals that you have in your data set go into training. And those 60% are in no other data set, no validation and no test set, okay? And then you have 20% that go into the validation set and then 20% that go into the test set. And so this, like, if you do this split right away in the beginning, you're not running into any of these issues and you're doing a really cool study on human behavior. An exception, I would say, is if you're actually interested in identifying behavior change in individuals over time. So you want to say, I want to know the person's level of depression in week 1 versus week 10. You obviously want to learn based off of the individual as well. because you kind of want to predict changes rather than like general behavior. All right, is that clear? Okay, cool. Another special case is the leave one out. It's basically when you have a very tiny data set and you only have like maybe 45 people in your data set and like only 5 minutes of each person. So you want to just leave out a little bit of the data for validation and training, validation and testing, and you want to use most of your data for testing. So that just kind of means that your split here becomes very skewed towards the training set, but you still should have like a def and a test set, okay? Even if they're tiny. But that's kind of like one consideration there. Yeah, and this can get very costly if you have a lot of data, so you don't want to do this. If you have like 1,000 people, you don't want to run 1,000 times. Okay, so let's talk a little bit about evaluation measures. So how would you measure if a system's doing well? What's the most popular stuff? F1 score, accuracy, ROC, the receiver operating curve, and then like in that case you would also look at the area under the curve. And you would also want to know that the error is low, right? So that's very good. And but most of the time I would say that we would probably like to look at accuracy, and we're often tempted to just look at accuracy and would like to motivate why this is not a really good case. So oftentimes you have very skewed data sets that have like a lot of red dots and only like a few blue dots, right? And if you learn this model on just accuracy, this separating hyperplane here that separates all the dots from none of the dots actually performs better than this one that seems to learn a little bit, but it learns like very poorly as well, obviously because like there's not much to be had from these two data points. But at least it learns something about the data, and maybe these are outliers, but B would actually have a better performance in like the training set, or in it's just raw accuracy values. And you really, so yeah, we answered that one, but you really want to be sure that you utilize the right metric for your data set. And maybe oftentimes you're actually not interested in the majority class. You might just, you don't care about it because you already know like 99% of my data is that class. I want to identify the 1% that's not that class. So what you really want to be knowing is like, where are these points? So that kind of changes your focus of attention as well. So you're gonna have to make sure that you're paying attention to the right type of error. And we have here like the different types of error that you can make in a binary classification problem. So this is what we call a confusion matrix. In the diagonal, you want the diagonal to be huge. Like you want there 100 and 100. But that's often not the case. But you want these to be large values and you want these to be small values. And these two are different in their type of like problem of error that's happening. So this one's actually a false positive. So the system thinks it is a positive sample, or like falls into the 1 class and not the 0 class, but it actually is a 0 class, okay? And this one is the other way around. So we have type 1, type 2 errors, like false alarm, false rejection are different words for that. And you can also look at this like this kind of like Venn diagram where all the instances are in the square, the true negatives are out here, the really positive class is red, this circle here are the false positives, these are the true positive samples, and these are the false negatives here. Okay? So this is kind of like another representation of the same thing here. And with these TP, FP, etc., we can do kind of cool like stuff. So we can say we can classify, we can get the classification error. So false positives plus false negatives. So these are all the errors that I make divided by all the samples is my error rate. My accuracy is the opposite, where I have all the true samples on the top, and at the bottom all the samples. Okay. So that's accuracy and classification error. However, the accuracy, as we discussed, is often skewed, and we don't really always want to look at the at the mistakes or the error type to the accuracies at the same way, in the same way. So we need to find different options to do this. So we can define false alarms, misrates, and recalls, and precision. And these are giving us additional information. So we split up our types of errors and the type of correct classifications into these more precise classes. And with these recall and precision, for example, we can do now like kind of cool new error rates. And on the one hand side, you can do a cost error rate where you can define different cost weights for the different types of errors. And you can also do what we had earlier in the front, the F1 measure, which I like very much because it basically combines both the ability for a model to recall your data. So whatever data goes into the model, is it able to like find, and how many of those does it find to be positive? And it also gives you like how many of those were actually like, but how is this relationship of recall related to the number of times it says yes, right? So recall can be super high, and if precision is super low, then that means that this is also pretty bad, right? But if recall is super high and precision is really high, that means that your model is doing really well, okay? And you can have the opposite as well. You can have high precision but very low recall. So that would mean like it is very, very specific to your data set. So specificity is high, but your sensitivity is low. And if this is super high, your sensitivity might be very high, but your specificity doesn't necessarily need to be high. So this is a nice measure that combines both of those together. So that's very successful. So we only have like a few minutes left, but I would like to show you a couple of, are there questions to this?
Could you please repeat the last part?
Okay.
Sensitivity and...
Is that just other words?
Yeah, I didn't get what the...
So, do I have it here? Basically, so in medical testing, they use the words specificity and sensitivity for their medical tests. So if and they use those terms to specify like the overall use of those measures, and what you ideally want to have both of those measures to be super high. So sensitivity means like if I take a blood sample test from you and run it through the test, like if you have the condition, how likely is my test to like set an alarm off? Okay, so yes, you have it, right? Okay, so that might be like you got the condition, okay? But then if the specificity is low, it might say yes to everybody, okay? So you want to have, and this is just the basically the precision and recall. So I think it's the specificity is precision, but sensitivity is like 1 minus recall or something like that. I gotta look it up exactly, but it's not very like important. It's just different words for those things. Okay. All right. So for like some machine learning experiments, I highly recommend looking into the scikit-learn toolbox. You can find it online if you Google for scikit-learn. It's in Python. They have fantastic, and I need to mirror this because I don't see anything. They have a fantastic documentation and tons of examples. So here, for example, we got a recognizing written hand digits example. So we have this is like how the training data looks like. This is our test data looks like. It can produce really nice outputs of performance, including confusion matrices, F1 score, recall, support, etc., average, and so on. So this is a really nice system to help you find good like models and parameters. And so what you would like to do here, I'd just like to walk through what's going on in this code here. So basically, this is just importing the ability to plot out these cool things here. Then sklearn, so this is your scikit-learn. You import data sets. You import the type of model you would like to use. So in this case, it's an SVM. You can import SVR, which is support vector regression. You can import neural networks, and so on. But then you also import like your different types of metrics. So you can like call the model to give you accuracy or F1 score, and so on. The very neat thing is that it has data sets inside the package, so you can basically download your data set by just calling this. So in this case, it downloads MNIST handwritten digits for you. This is just to show a couple of them, I guess. But then what is important here, so you assess the number of digits that you have, and now you they kind of, so this is kind of like just giving you the number of samples that you have. Reshape your data, not so important. This basically means that the network doesn't get a square input, but a line input, okay? So humans care about that numbers look like this, but machines don't care about if I take the first row and then put the next row next to it, because machines don't know the concept of numbers, right? So they don't care if it's like a nice square and if it's actually written how it's written. So that's why they reshape it there. So that's just a minor thing. SVMs like vector inputs. They don't like matrix inputs, okay? Then you basically create your classifier, and here we have a hyperparameter, okay? And you can have many more. We can click on this and I can show you what different hyperparameters we have. But then we fit our training data with the model, and in this case they basically use half of the training data for half of the data for training and half of the targets for training, and then they define like what the labels are for the prediction. So these are half of the future targets that we want for the test, and they predict those samples with the support vector machine, and basically they just report after what's happening here, okay? So if you want to use a different gamma for the next iteration, what would you want to do in this case? So you either just run the whole thing again and then like report on whatever the best performance is on a test set, and you can run it again and again with different parameters. But the right way to do it would be to go up here, load your digits, resample them or reshape them, and then you define training set, def set, and test set. Okay? And then you create the loop over all the hyperparameters that you want to test. So you say like for gamma in, and you create a list like 0.001, 0.01, 0.1, and so on, right? And then you loop it over and you compare like which one's the best, you identify the maximum validation performance, and then you use that on the test set, okay? So that's kind of like how you would have to change this setup to follow kind of like our rule. Let's see what kind of like hyperparameters they have. So you can just click on these things up here. So this is like it's called a slack variable that basically we'll talk about this. This allows you to tune how much penalty the SVM gets if it allows certain data points to be like within the margin. We had the discussion about like what the maximum margin is, and if you can define a maximum margin with some variables that fall inside it, but this one punishes that. If you can crank this one up to very, very high, like even infinity if you want to, then you would not allow any data point to be in the margin, but that might also mean that your margin becomes very zigzaggy, okay? Then you define a kernel, so it could be RBF, could be linear, could be polynomial. Polynomial would have the variable degree. I don't think that the RBF actually uses this parameter. You can let the gamma to be auto-selected for you. This is kind of neat to do. And so on. So you see already there's like a whole bunch of hyperparameters. And if you want to test all of them, like right away, that it will take a while, I think. There are other options here, so like you can actually also like search for stuff. You can search for cross-validation. You can get like a nice cross-validation help here from this the scikit-learn. Where's the cross-validation? Yeah, so here basically it tests your data. It splits your data into train and test splits. But again, in our case, like, be careful using those predefined toolboxes for your cross-validation and training split, because they don't have, like, and this is something in the machine learning community that I'm completely baffled about. Like, nobody cares about speaker independence. Like, we're like in the fringe world of machine learning. They don't really allow us to define grouping parameters that are used for splitting, or at least I haven't found it yet. So you want to make sure that if you use that every single data point in your matrix comes from a different person. Okay? Then you can use this. But if not, you're gonna run into the problem of like probably overfitting on the individual. All right? So yeah, this is very handy, and I have not run into any situation when I had a question about scikit-learn and I could not find an answer on Stack Overflow. So this one's like the most used and the most popular machine learning toolbox out there right now. MATLAB has a number of really cool things as well. So for example, you can say doc classify, that gives you a nice documentation about the function classify in MATLAB with tons of examples and neat visualizations. You can say doc, what is it, SVM classify? CSVM. No. Look for SVM. And these are cool functions in MATLAB. You can use those. Oh, it's doc SVM classify. And then here you have your MATLAB support vector machine with cool visualizations. You can learn how these separating hyperplanes look like. The circles around here, these are the support vectors. And here you see these guys that are on the wrong side of the hyperplane. Those violate the margin, right? And these two violate the margin too. And if you crank up your C parameter, it would learn something like this, right? If it has the power to learn that. But so these violate the margin, and so just for you, so you know that this is kind of like how you can visualize what's going on. These are your test samples in this case, so they get correctly classified. So there's a lot of really cool stuff here. I encourage you to explore it. Both scikit-learn and MATLAB have options of visualization, training, testing, and so on. Play around with the stuff, and I would try to get a feeling for what's available. I think scikit-learn has more things available, and it also interfaces nicely with the new modern deep learning toolboxes. So there's a toolbox called skFlow, which is basically scikit-learn TensorFlow in scikit-learn kind of type language, so you don't have to deal with tensors too much. You can basically use your matrices that you have in scikit-learn and so on. So that's really cool stuff. I think it's worth exploring a little bit. Let's get back here in 5 minutes. Or, 5 minutes.